Hello guys, in this video I will introduce the solution for LeetCode weekly contest 3, 4, 5. There are 4 problems with difficulties 3, 4, 5, 5. And we start with the first problem. So for this problem, it will find the loser of the circular game. The problem looks like this, that we have n friends that playing a game. The friends are sitting in a circle, and their number is from 1 to n, clockwise order. And so we also provide another value of k. And in the first round, the first friend will pass it to the friend who is k steps away from him in the clockwise direction, and then that friend will receive the ball, will pass it to the friend who is 2k steps away from them in the clockwise, and the friend who received the ball should pass it to the friend who is 3k steps away from them in clockwise direction. And this game will stop if a friend receive the ball for the second time, and the loser of the game are friends who did not receive the ball in the entire game. And we should return a vector to have all of the losers of the game. And the solution is just like, we can just simulate the process and use this vector to record which friends is visited during the game. And if this means some friends receive the ball the second time, we just break. Otherwise, we just flag the position as visited, and then we pass this variable with k. That's because for each round we will add k to the steps, and when we break out, then we just check which friends is not visited and push them into the answer vector, which will be returned as the result of this method. So this is the first problem. And the second problem, this problem is we have a zero index array derived with length n. Is derived by computing the bitwise XOR of adjacent values in a binary array, original of length n, especially for each index I in the range 0 to n minus 1. If I equals n minus 1, then derived I equals original I XOR original 0. Otherwise, derived I equals original I XOR original I plus 1. Given an array derived, your task is to determine whether there exists a valid binary array original that could have formed derived. Return true if such array exists, or false otherwise. A binary array is an array containing values 0 and 1. So for this problem, actually we can think about the problem like this way. So first of all, this is an integer, right? So integer may have multiple binaries, right? But we may just consider one binary. So what I mean is that for an integer, let's say it may have multiple binaries. For example, it can be it can be, for example, like this, right? So for this integer, it have five binary bits, but we may just check one at first to understand how this problem is resolved. And so, for example, this is the first number, and for the second number, right? So here it can be 0 or it can be 1. And the same thing for third problem. For third number, it can be 0 or 1. And for example, we have 4 numbers totally. The 4 number will also can be 0 or 1. And for the fourth number, it will do XOR with the first number again. And we can think about we have the derived array. So that means if derived array is 1, then that means the original number, the bits should be different. So that means if previous bit is 0, then now the bit should be, next number's bit should be 1. If previous number's bit is 1, the next number's bit should be 0. So this is about if the derived array's number is 0, and if derived number's bit is 1, right? So if derived numbers bit is 0, then what it means that if the previous number is 1, then the current number bit should also be 1. If previous number bit is 0, then current number bit should also be 0. So this is about the case that derived array's numbers bit is 0. So we can see if we define the original bit of the first number, and based on the derived numbers bit, we can always decide what is the bit of the next number, and so on. And another problem is only when we have the bit value of the last number, and we need to check whether the last number's bit and the first number's bit, whether they are compliant with the derived result. So if it is compliant, then the result is true. Otherwise, the result is false. So here we can see for the codes. So here we check at most 20 bits. That is so this is decided by the constraints here. That n maximum value is 10 power 5. So 20 bits is enough. And for each bit, we just first of all, based on the derived numbers value. So here we check whether derived numbers bit is 1 or is 0. So if it is 1, then I just change the bit value. So if its previous is 1, then I change it to be 0. Otherwise, if previous is 0, I change it to be 1, and so on. And after this, I will check the last derived numbers bit. If it is 1, and if current value is 1, then that means it's not compliant, because the value will start with 1, and if derived number is 1, so that means current value should be 0, but current value is 1, then that means this result is not, so this value is not compliant with the original value we started, that is 1, so is good is false. On the other hand, if derived numbers bit is 0, so actually that means we should have same value with the started value. that we should have value 1, but if value is 0, so that means it is not compliant. We also set it's good as false. And finally, we just return it's good as a result. Okay, so this is for the second problem. For third problem, we want to find the maximum number of moves in a grid. The problem is like we have a m by n matrix grid consisting of positive integers. We can start at any cell in the first column, and traverse the grid in the following way. From cell, row, and column, we can move to any of the cells. Row -1, column +1, row columns +1, and row +1, column +1. So that means, for example, from this cell, we can move to this cell, we can move to this cell, we can move to this cell. So there are 3 cells we can move at most. And we also need the value of the cell we move to should be strictly bigger than the value of the current cell. Okay, so that means in the 3 potential cells, if any cell's value is strictly bigger than the current cell, then we can move to that cell. And in this case, we want to get the maximum number of moves we can perform. Okay, so for this problem, other than we check from the beginning to the end, we can check in the reverse direction. So what we can do here is, for example, we have this. We have just use the first example. So we have 4 by 4 matrix, and we already know the value of each cell, right? So we just start from each of the cell in the last column, and from this cell we go to check like all of the cells in the previous column it can reach to this cell, right? So there are 2 cells that potentially they are possible to move to the current cell, and then we go to check whether this cell's value is strictly bigger than this cell. If it is, then we use this cell's steps. So first of all, we initiate all of the cells steps at 0, and also this is all of the cells steps is 0, 0, 0, 0, 0, 0, 0. So this means moves, right? So currently all of the cells don't have move, and then I go to check whether this cell's value is strictly bigger than this cell. If it is, then based on current cell's move number, and go to update this cell's move number. So for this one, current cell's move is 0, then I update this to be 1. So that means from this cell I can move one step from this cell to this cell, right? And also same thing, that I go to use this cell's value and move number to update this cell's move number. And if it cannot move from this cell to this cell, then we just don't update move numbers here. And same thing, like for each cell in the last column, we go to check all of the cells that we can reach to current cell from previous column. We use this cell to update their moves number, and we always update to assign the previous column's cells move number with the maximum that the possible maximum moves number we can get based on the current cell's move. And after we use this column to update this column's cell, and the same thing that we use this column's cell to update the previous column's cell, and so on. until we update the first column's cell, and then we go to iterate all of the cells in the first column to get the maximum moves in the first column and return that result. So this is the code. Like the first of all, this is the steps. That means so how to construct a matrix of size m by n and initiate all of them move number at 0. And then here I iterate from the last column to the first column, and just iterate each cell in that column, and go to check. So this is go to check the cells on the left upper direction, and this if go to cells on the just on the left, and this is go to check the cells on the left lower direction. So this is go to update all of the cells that is possible to reach to the current cell. And finally, here I go to check the maximum moves count in the first column and return the result. Okay, so now we go to the last problem that we are given integer n, and there is an undirected graph with n vertex numbered from 0 to n minus 1. And we are given a 2D integer array edges where edges I equals ai bi denotes that there exists an undirected edge connecting vertex ai and bi, and return the number of complete connected components. So completed components means there exists a path between any two vertices, and no vertex of the subgraph shares an edge with a vertex outside of the subgraph. So that means if any node is have a path with the current subgraph's vertex, then it should belong to the same connected components. And also, we call a connected component is complete if there exists an edge between every pair of its vertex. So such like this is a complete connected components, and this is also a complete connected components, and this is also one. So the problem is we have this graph, and we need to return the number of completed connected components in this graph. So for this one, we make use of the data structure and algorithm called joint united find algorithm. So actually you can Google this. This is quite a popular, and it's also a standard algorithm. It just go to it's just go to resolve the problem like we have multiple components, and then with this algorithm we can union some components together, and so such like I can union these two. I can also union these components with them together. So these three components are unioned in one side, and I can also union, for example, these two components together. So here I have three sides, and also if I have two components, I can quickly get the result like whether they are in the same union or not. So this is some kind of data structure and algorithm to resolve the problem. Actually, you can go to check like union joint, union maybe union find. Yeah, this joint set data structure, and union find algorithm is something like this. So we just make use of this algorithm, and the idea is for each of the edge, right? So that means, for example, if there is a, for example, this is a graph, and if there is a edge between two vertex, that means these vertices are in the same union, right? So here I get nodes, and I check whether they are already in the same union or not. If they are in the same union, I just update this union's root vertex edge number by 1. So that means, because there is a such like if I select this vertex as root, right, and there is already a union, and if I have another edge here, so that means, for example, like no, so it looks like this. For example, this is the current graph. I have edge between, for example, this I call vertex 1 and vertex 2 and vertex 3. So there is already edge between 1 and 2, and also there is an edge between 1 and 3. And now I also have another edge between 2 and 3. So, and here I go to check whether vertex 2 and 3 are already in the same union. So now they are in the same union even before I add this edge, right? Because they are already connected together, so they should be in the same union. And in that case, I just say there is another edge added in this union. So this is the node. I just use this root to record how many edges in this union. So that is why so this is find the root of the union, and I use this vector to record how many edges in this union. And if node 1 and node 2 they are not in the same union, then what I do is, I first of all I go to find node 1's, so current node 1's union's edge number, and current node 2's union's edge number, and then I unite node 1 and node 2 together. So with this operation, node 1's union and node 2's union, they are connected together with a new union. And also, after I united them, I find the root of the current union, and then use this the vector to record the current union's edge count as previous union 1's edge number, and previous union 2's edge number, and plus the new edge. So this is the current union's edge number. And actually this is not really used. So I just record this. And after this, I go to iterate the roots, right? So let me see. Yeah, so here I have a map for roots. So for these roots, it's just for each of the vertex in the graph, I find what is the root number, what is the root vertex of the union that current vertex is in. And after I get this root count, I just go to check whether this root is already recorded. If it is already recorded, that means the count of root nodes is bigger than 0, so it means this root node is already in the roots, then I just plus the current roots value by 1. Otherwise, I initiate the root nodes. So this operation will add this root node into this map, and also the value will be 1. So this root map, the key is actually the root vertex of each union, and the value is how many vertex in the union. So after this, I have the first of all, how many edge number of each union, and also I have how many vertex count in each union. And based on this, because for a complete connected components, we can see, for example, we can see how many edges we should have based on the vertex count. For example, if there is only one vertex, then expected edge number is just it's 0, right? Because there is no edge. And if there is 2 vertex, then the edge count should be 1. And if there is 3, the edge count should be 3. And if vertex is 4, so we can see when we add another node here, then it should have a edge with each of the other 3 nodes. So this should be, this should be 3 plus 3, right? So we can see the rules to calculate the expected edge count is like this. If we have n nodes, if we have n vertex in a complete connected components, right? If there is n vertex, then we can see, first of all, we can calculate any 2 vertex and connect them together. So we have 1. And then when we add another vertex, then it should have connections with the 2 vertex. Then it should plus 2. And then when we add another node, then it should plus another 3 edges. So it's plus 3, and so on. And finally, what is the final nodes? After we add the final vertex, then how many edges? It should be n plus 1. Sorry, n minus 1. Okay, so we can see how we calculate the expected edge count for complete connected edges. So it's 1 plus n minus 1 by n minus 1 and divided by 2. So if our edge in a union meet this result, then that means this is a completed connected component. Otherwise, it is not. So that is why I calculate so here I get the root count of each union, and I get edge count of each union, and then I check whether the edge count is equals with the expected edge count of a complete connected components. If they equal, then there is a new complete connected components. I just update the answer and return this answer. Okay, so this is the last problem. If you have any questions about any problem, please let me know. Thank you.